Okay, so welcome back, and we're going to be looking at galvanic cells this time. And a galvanic cell is essentially the beginning piece for like a battery. And there are certain rules that we got to follow when we're trying to put together our galvanic cell. And so we've got an example problem here. What is the cell potential of a galvanic cell using tin and zinc electrodes? So we'll just deal with that part of the question for right now. When it comes to cell potential for galvanic cells are going to spontaneously move electrons when the cell potential for the cell is positive. So as we look at this situation, we're going to need to go to a reduction table. Textbooks have them, College Board puts one out, so they're relatively easy to find. I think we'll go with the College Board's reduction table. And so what we find when we're looking at the College Board's reduction table is that we've got two options for tin. We have a tin 4 plus 2 electrons becoming tin 2 plus. So 2 electrons, that's just awful. Alright, so becoming tin 2 plus. Problem is, we want to have an electrode. To be an electrode means a solid. This half reaction isn't going to work because we're going to have two aqueous ions. So let's go back to the reduction table, see if we can find tin solid listed. And I do. And Sn2 plus 2 electrons yields tin solid. And then the other one that we were going to work with was zinc. And so the half reaction for zinc that I find on the reduction table is Zn 2 plus 2 electrons yields Zn solid. Hopefully you won't get confused on my S's and my Z's, but with that being said, in the reduction table there's also a standard cell potential listed, and the unit on these is going to be volts. And so for the tin half reaction we've got negative 0.14 volts, and for the zinc reaction I'm seeing negative 0.76 volts. Now again, my goal is to have a positive cell potential. Alright, that is what's going to allow the electrons, those two electrons that are being given or taken up by the tin or taken up by the zinc, one of them is going to have to change its perspective. But the two electrons being transferred in essence, and we know that because these two numbers agree. So two electrons are definitely being transferred. When I put these half reactions together, I need to get a positive potential. What that means is that one of these two half reactions is going to have to be flipped. If I flip this one, I'm going to be putting positive 0.14 with negative 0.76. Results still negative. But if I flip the zinc half reaction, I get positive 0.76 with a negative 0.14. Adding those two together would give us a positive result, which means that this is not the correct perspective for the zinc half reaction. Instead, I need to flip it where I now have this. So, a couple things we can take from this. I'm going to even write in the positive 0.76 volts. So, this is the reduction half reaction because I'm going from 2 plus down to a 0 oxidation state. This is the oxidation half reaction because I'm going from a 0 oxidation state up to a 2 plus. So this now gives us the opportunity to add together our cell potentials, and so got 0.76 plus a negative 0.14, looking at a standard cell potential for this galvanic cell of 0.62 volts, and I'll even put in the positive to remind myself. So positive 0.62 volts. So that is going to be the cell potential of the galvanic cell. Because what the galvanic cell is always going to do is it's going to arrange itself in a way to have a positive cell potential. So it doesn't necessarily matter what you're putting into the cell. The pieces are going to work in the direction that gives a positive cell potential. So now we've been asked to also write the balanced equation for the cell. We have identified the half reaction that needed to be flipped, so we have our pieces here. And so to an extent, we can follow the cancellation rules that we've been using so far this year, which means that SN2 plus, I'm going to look for something I can use to cancel with SN2 plus. SN doesn't cancel, it's not exactly the same. ZN2 plus, not exactly the same. 2 electrons, not exactly the same, which means that for the balanced equation, I can start off with SN2 plus. Now, as I move through, I find that the next reactant I have to work with is 2 electrons. I've got 2 electrons on the reactant side, but due to flipping this equation, I also have 2 electrons on the product side, which means that these 2 electrons are going to cancel. So therefore, they don't get a chance to come across. So now I go to the next half reaction where I have zinc listed as a reactant. Do I see it elsewhere, anywhere? Nope, not as zinc solid. I've got a zinc ion or I've got tin solid. So that means zinc solid also gets to get written down. Now I'm going to look at my products. And I've got tin as a product. And again, looking around, there's not the exact same tin listed anywhere in these half reactions. So tin solid gets listed as a product. And the zinc 2 plus ion also will get listed as a product because I don't see its match anywhere else. And so, having determined which half reaction, so basically the build-up here to get to the balanced equation is I needed to determine the half reactions that I was going to utilize. Because I knew what my electrodes or what my solids were going to be, that gave me a guide in terms of picking out the reduction half reactions to use. Then I knew that I was going to have to flip one of my 2 reduction reactions. And the one that flips is the one that's going to give me a positive result when I add the 2 potentials up. So it turned out that the zinc half reaction had it to be flipped, turning it from reduction into oxidation, giving me a positive voltage. Once I then had my properly written half reactions, I could then look to get things to work out to cancel. Now, the nice thing is, a couple things worth mentioning here. If I were to change the magnitude of this half reaction, in other words, have 2 tin plus ions, 4 electrons, 2 tins, it doesn't do anything to the cell potential. So this is not like Hess's law where doubling the half reaction would double the cell potential. That's not the case. So cell potential is an intensive property. It's going to stay unchanged as the magnitude of the half reaction is adjusted. So it's possible that if you have one reaction with 2 electrons and then another reaction with 3 electrons, you know that the balancing is going to be 6 electrons. So you're going to have to adjust the coefficients in this half reaction as 3 times, and you know you're going to have to adjust the coefficients in this reaction as 2 times so that everything can equal out to that 6 electrons that's needed. But again, that's not going to have any effect on the cell potentials that would be written down. So there's no 2 times multiplier times the cell potential. The multiplier only happens with the half reaction. So with that being said, we'll go to the last piece. Write the balanced equation for the cell. We've done that, and so now on to, sketch the galvanic cell. So when it comes to a galvanic cell, we're going to have an anode and a cathode. Now typically, the way that I think about things is I always put the anode on the left, because when I'm reading, when I'm doing things, I tend to work from left to right. And so that's the first piece to think about is this. You're going to have, in the anode, you're going to have an electrode. That electrode is going to need to be a solid. So as we look at this, we have to determine what reaction's going on in the anode and what reaction's going on in the cathode. What I have here is my flow of electrons indicator. In other words, for a properly constructed galvanic cell, the electrons are always going to flow from the anode to the cathode, which means that the anode is going to be the half reaction that is releasing the electrons. So if I come back over here to this section, I find that zinc was the half reaction that was releasing electrons. So therefore, this is going to be a zinc electrode. That means that in solution, I'm going to have zinc 2+ ions. So I can call this aqueous, and we can remind ourselves that this is a solid. Right now, electrons are only able to flow from the anode to the cathode. So one other piece that I'm missing is what's known as a salt bridge. There's also what's known as porous discs. But you need some mechanism by which the electrons that are being transferred from the anode to the cathode can find their way back from the cathode to the anode. So you need some salt bridge. Otherwise, what happens is pretty quickly you get a buildup of negative charge in the cathode and positive charge in the anode, and it gets very hard for those electrons to make their way across the wire in from the anode to the cathode. In other words, it gets very difficult to make the electrons flow. And that flow of electrons is essentially the current. So continuing on, taking a look at the cathode, we've established that the reduction F reaction is going to be the one that takes on electrons. So that would be the best fit for the cathode. And so what we see here is that according to the reduction half reaction, tin solid is going to be the electrode, and tin 2+ ions are going to be in solution. And so really those are the major pieces of the galvanic cell. You've got to have something in solution, you need to have a solid electrode, you need to have a wire connecting the anode's electrode to the cathode's electrode, and then again you're going to need to have something in solution so that you can have a transfer of electrons. So in other words, as zinc turns into zinc 2+, electrons are going to move along the wire, leaving the bar of solid zinc, move along the wire. They're going to interact with the atoms of tin that are in the electrode over here, and as those electrons are taken up here or added to the bar of solid tin, what's going to happen is those electrons are eventually going to make their way to a tin 2+ ion that's in solution, and that tin 2+ ion that's in solution will join the bar. And so what we would see over time is that the mass of the zinc electrode would decrease while the mass of the tin electrode would increase. So the last piece to make sure that I've made clear is the reduction half reaction belongs in the cathode, and the oxidation half reaction belongs in the anode. Now if you want to take a closer look at some of this potential calculating, I'm going to put together a separate video, so you can go ahead and take a look at that separately if you want to go back and review that, these ideas of electrons not balancing out. The other thing to say is sometimes you may be faced with a half reaction that has no solids. We were fortunate that both our half reactions here had a solid component, solid tin, solid zinc. But if you're ever faced with a half reaction that does not have a solid component, I strongly recommend using a platinum electrode. Okay? But like I said, the two half reactions we dealt with both had solids, so we didn't need to go to that level. But if it ever happens that you don't have a solid present, all you've got is gas or aqueous or liquid, allow me to recommend platinum as your electrode of choice. So I hope this made sense. I hope this helps you out. Good luck putting it to use for yourselves.